Section classification. There are 4 types of section which is classified as per IS 800. This study in module 1 deals with plastic analysis. See, a material goes under different stages. First is elastic stage. You can see this is moment by rotation. You can relate to stress strain graph. This is equivalent to that. And you have moment at one point, and at x-axis you have rotation. If you are raising your moment in a structure, the beam will be having internal moment or stress. It will be keep on increasing when you increase the load. So eventually what happens, the moment will get increased. Slowly the elastic stage will go and it will go into elastoplastic stage, and finally it reaches the plastic stage, then it breaks. So this is the behavior of a material during a stress strain graph, and you would have an experience of doing tension test on mild steel. So when you are doing, the material gets elongated first and it goes to the next stage of 15 to 20% of elongation. The equipment or the material will get elongated. After that the material gets broken. So this is the stage. Okay, now in steel structure you are having a topic called plastic analysis. See, this is wholly covered in module 1. What is the use of plastic analysis is, the previous class I have given an example of how the structure should fail. Even though making a good structure without failure is one part, and deciding the structural how to fail is the next part. I showed you a picture which a long structure or a tall structure which is collapsing not immediately, but it is collapsing step by step. This is a mode of failure. You are directing certain type of failure, and this is known as the plastic analysis. So these 4 classifications which will be used in plastic analysis. Even though your structure might fail in earthquake, it might fail in the high wind. What happens during the failure? Certain members can fail. If you are imagining this classroom, if any failure is occurring, the failure will occur at the center of the beam. So that what happens, if the structure is failing at the joint, the column will fail and also the beam will fail. What happens? Total collapse will happen. So if any system has to fail, you have to make that only the particular area should be failed. That is, if the beam only is failing now, nothing will happen to the next beam and the adjacent beam here. Like that you have to design. So how to design and what is the theory behind that is called the plastic analysis. So this concept comes under the plastic analysis. So when you are designing a steel structure, you should check and you should design that under what criteria you are designing your member. So first stage is plastic. This is class 1. In IS 800 they have classified this stage as plastic, where if you are removing your stress or if you are removing your load, what happens? The member has to come to original place. This stage is called elasticity. If you are stressing any member and if you are releasing that force, it has to come to its original position. If it is not coming, then this state is called plastic stage and it takes higher moment. This is known as MP. This is plastic moment, and My is known as yield moment. So the highest moment which is achieved by the structure before breaking, this goes beyond the plastic, and you have 2 classes. The other class is slender. What do you mean by slender is, even though the column might be under elastic stage, but what happens, the column supposed to buckle. What do you mean by buckling is, if you keep on load your column, what happens, it tends to bend. So if you are keep on loading in compressive mode, what happens, at a particular point this column tends to buckle. So it tends to attain a curved shape. So this is known as the buckling failure. See, this is under elastic stage. If I am removing the load, it comes to original position. This concept is known as buckling. So can you allow buckling in your structure? No, nobody wants their structure to get buckled and all the people are evacuating that place, it comes to the original position. So nobody will like that. The column should be stable and it should be stiff, whatever might be the thing. So this area is known as slender area. You can design your column to slender limit or you can design your column to a plastic limit. If you are designing to a slender limit, what happens? If you are keep on adding load, your column tends to buckle. It might be in elastic stage. We are not allowing this kind of failure. So that is why the plastic analysis is studied in the steel structure. And there is the two intermediate components, that is class 2 and class 3. These are compact stage and semi-compact stage. What do you mean by that is, if your local buckling can be avoided, so you can avoid this buckling by making it into semi-compact or compact section. If it is not coming under these two limits, then it is called a plastic section. This can be done by, when you are designing your structure, you have to set your limit for width to thickness. So what is the thickness of your element? What is the width of your element? If you know these two parameters, you can make your structure to a elastic limit or plastic limit. So you can class your structure what you are designing. When plastic analysis is used, the member shall be capable of forming plastic hinges. So this is what I said, the plastic hinges will be formed at the joints, wherever you have beam column joints and at the place you have load. So if any load is there, a point load is there, then at that point you will be having the plastic hinge. What is plastic hinges? When the structure is failing, the structure fails at the place you have hinges. So this is the understanding of section classification. Okay, the table 2 purely discuss about the classification of your section. In 18 you have table 2 and this table represent limiting width to thickness ratio. You can make your structure to plastic classification and you can design your structure for plastic failure, compact or semi-compact failure. If it goes beyond semi-compact, then the structure is called slender. You can check that why the slender section is not available. If it does not comes under these three sections. Now how to make these four classification is by selecting the width to thickness ratio. So this is what it is given in first criteria, outstanding element of compression flange. So if you are having any shape like this, take an example of I section. You have three number of section which is having width to thickness. What is the width here? Which will be known in B, and you will be having thickness here. Also, this is the thickness of the web and this is the total width. When you are designing your structure, you should be selecting this component, that is width to thickness. Okay, for a rolled steel section, the breadth to thickness of the flange. What is the formula? The ratio is given here as breadth to thickness of the flange. So what is breadth here? So you have the breadth and you have the thickness. You have to divide the breadth by this thickness. So if you are dividing, if your answer comes below this range, that is 9.4 epsilon. What is this epsilon? Here it is given. See, this is strain 250 divided by Fy root. So this is your formula. What do you mean by Fy here? Yield strength of the material. So if you have yield strength of 250, 250 by 250 will be what? 1 and root of 1 will be 1. You have to substitute 1 here. So 9.4 into 1 will be what? 9.4 only. If breadth to thickness of the flange is equal to 9.4, then your section will be plastic. If you are designing your section like that, if the section is failing, it fails under plastic mode only. It will not get buckled. Your section will not get buckled. So if you want to overcome the buckling failure, what you can do? You can do for design of plastic. Okay, if you are designing for 15.7 epsilon, so your epsilon is 1, take an example. If breadth to thickness of the flange equals 15.7, if your answer is getting more than 15.7 in the sense, your structure will fail by buckling. So whenever you are loading your column, what happens? No plastic hinges will be visible. Even when your load is there, your column tends to buckle. So when you are designing itself, you can check about the behavior. So this is the use of that. So you have different kinds of section like that. That is welded section. This is rolled steel section. What do you mean by rolled steel section is, these are the example of rolled steel section, where you can directly purchase from the supplier, you can directly purchase that. No need of welding. If you are welding in your shop, if you are taking two components, that is a plate, and if you are joining another plate, and if you are welding, in the sense you are making your own plate, and this comes under the welded section. Rolled steel section is directly acquired from the supplier and which is made by casting, which is known as rolled steel, and this is welded. And another criteria is internal element of the compression plant. You have outstanding element and internal element. Okay. Also for the classification of web and I, H or box section. So if you have these kind of section, you can use depth to thickness ratio as this formula. So by this table, whenever you are designing, you will come to know that. Just as of now, you understand that you can design your structure on how it should collapse. So this is the idea of this topic. When you are designing your element, say for in module 2 and module 3, you will be knowing in detail. So as of now, you understand this concept. So there are this much of section which is available. So what is the name of the section? Rolled, beam and column. So this section is I section. This could be used for beams and columns. This is rolled steel section, and this is a channel section, which is rolled steel channel, so which will be in C shape. This is called channel section, and this is called hollow rectangular. You will be not having any content here. There is no material here, only hollow part will be there. This is a hollow circular. This is angle. What is known as back to back angle? If you are having two L section and it is connected in back to back, then it is known as the back to back angle section. So these are the technical terms. Okay. This component is known as built up section. What do you mean by built up section is, you are connecting plates. So this is a separate plate. You are connecting 1, 2, 3. You are connecting these 3 plates and welding. So you have a small dot. Yes or no? Can you observe the small dot? These dots are welded area. You can connect the plates and you can weld it. Why you want, sir? You can ask a question that, sir, I have in shop itself this section is available. Why do I want to purchase and why do I want to weld? When you are designing your building, light sections are okay and it is enough. When you are designing a bridge, go and observe the bridges where you have the much higher depth. So you will be having 1.2 meter height or 1.5 meter height. More than your height, you will be having a beam. So those kind of beams are not available through any supplier. You have to do, you have to purchase the plates, build it on the site or in the shop. So you can do these kind of sections. These are all known as built up section. Take a channel section. This you can observe that this is a channel, that is C section. You have a plate and another plate. With the 2 plate and channel section, you can make a built up section. Okay. These are some of the examples. So when we are discussing in the problem, we can look into this detail. Take this concept, plastic behavior of steel structure. It is structural steel. What do you mean by a plastic behavior is, see, you have I section here. See, this is a beam. If you are loading it, what happens at the top? You will be having compression. At bottom, you will be having tension. Yes or no? Okay. This is the first state. If you are loading your structure and this is within the elastic limit, what happens? Your moment will be lesser than my. What do you mean by my? Y is known as yield and m is known as moment. That is yield moment. When your moment is lesser than the yield moment, what happens? Your section behaves like a elastic stage. If you remove the load, your section will come to the original position. Okay. When the material achieves the moment equals the yield moment, that is the critical point. When you add 1 kg or 2 kg, after that your structure will not regain its original position. Okay, this is the borderline state, and when your material comes to plastic stage, what happens? Your moment will be attained. You can see the straight line here. You can see a tapered line. When your object behaves in a yield limit, it will be this kind of the stress strain graph, stress strain behavior. When your material achieves a plastic stage, the moment will be achieved throughout its section, and when the material entirely reaches the plastic stage, what happens? You will be having top as compression, bottom as tension. Both the stress area will be equal. So this is known as the plastic behavior of steel. Okay. Now at this point it is known as MP. What do you mean by MP is where you write it. M is known as the moment applied and My is known as yield moment and MP is known as plastic moment. The moment in your structure goes beyond the yield limit and it goes to plastic stage. So this is what I have highlighted. During the stress strain graph, you have these stages. When the material is under the elastic limit, which is called elastic stage, and this is known as the strain. So the strain will be very much less, and when you keep on increasing your stress and when you keep on increasing your load, the material gains to next level known as the elastoplastic range, and if you keep on further adding some load, what happens? It goes to strain hardening. So strain hardening is the last point, and after that you will be having the breaking point. So this is the level. This is the elastoplastic stage where you have the change of elastic and plastic stage. So this area is called the elastoplastic area. When it crosses that, this stage is called purely plastic stage. My is yield moment. How to find yield moment? ZE. What do you mean by ZE is elastic section modulus. What do you mean by Z? Section modulus. Elastic section modulus into Fy. So if you find this, you can find My. When you are solving your problem, these components will be very much useful. And what is MP, which is known as plastic moment? What is the formula is Zp by Fy. Note here that there is only one change. What is the change in this formula? You have Fy the same. If you substitute Ze, that is elastic section modulus, you will get My. If you substitute Zp, that is plastic section modulus, you will get plastic moment. So this is the difference. So you have two types of moment. What are they? Elastic moment and plastic moment. So the moment which is attained within the elastic stage, which is called Me, and the moment which is achieved in the plastic stage is called MP, that is plastic moment. How to find Zp is, you can find by this formula A by 2. What is A? A equal to A1 plus A2. What are the areas? When you are dividing this section into two components, this is known as the centroid. Above the centroid you will be having one area and below the centroid you will be having one area. If you add these two area, you will be getting the total A. At the plastic stage you will be having the same area, that is A1 will be equal to A2. If you need Zp, you can find A by 2 Y1 bar plus Y2 bar. What is Y1 bar and Y2 bar is? Take an example. This is a oval shape. You can find Y1 as, this is the first half. Take this first half, find the centroid, and from the centroid to the equal area axis, This is equal area axis, which is known as y1. From the equal area axis, you find the centroid. From centroid to this another half, that is y bar 2. If you find y1 bar plus y2 bar into a by 2, you will be getting zp. So during your problem, this formula is very much important. How to find zp? A by 2, then y1 bar plus y2 bar. This is your formula. If you have this kind of I section, see this I section is not same. When you cut this section in x axis, you will be having different shapes. So when you have this kind of section, you have to cut the section in equal area. What do you mean by equal area is bottom and top half should be having same area. If you cut at this point, what happens? You will be getting two shapes, and you can find from the equal area axis to the centroid, which is G2, and from equal area axis to first section of G1. This distance is called y1 and y2. The top part is called compression and bottom part is called tension. This section is called unequal I section. So in your problem, if you need to find ZP, that is plastic moment, MP, this is plastic moment, you have to find Fy into ZP. What do you mean by ZP? You have to find A by 2 y1 bar plus y2 bar. This is your formula. You can find y1 and y2 bar by cutting the section into two equal half components. And what do you mean by shape factor is the ratio between MP and My. What is MP? Plastic moment. P for plastic, M for moment. Plastic moment divided by yield moment. So what is shape factor? Just you have to divide the answer. What are the answer? MP by My. It's a property of a cross sectional shape and it is independent of material property. This ratio is known as shape factor and it can be indicated by the letter V. Shape factor can be indicated by the letter V and the formula is given here. Shape factor is similar to moment of inertia. Moment of inertia doesn't care about the material property. The same way, shape factor also doesn't care about the material property. It depends on the shape. Whatever your shape is your cross section, it gives the possibility and advantage of the shape. So the shape factor why we are finding here is if you are designing your structure for plastic stages, you have to know shape factor. If you are designing your structure within elastic limit, what is enough? Moment of inertia is enough. If you are designing your structure for more than elastic stage, up to plastic stage, if you are designing, what is enough? Shape factor is important. Without shape factor, you cannot find the MP. What do you mean by MP? Plastic moment you cannot find. Okay. For a conventional shape, for wide flange I section, flexure above the Z axis, the shape factor ranges from 1.09 to 1.18. For all I section, if you have I section, it might be all combinations. The answer will be around 1.09 to 1.18. When a problem is given, if your answer is not within the limit, you can check that somewhere you have done some error. And for an average value about 1.14, you will be having at an average value of this 1.14 for I section. For wide flange only. Okay. For a rectangular shape, you will be having the shape factor of 1.5. For all the shapes, you will be having 1.5. Now in this topic, we will be knowing the collapse load. What do you mean by collapse load is, see by this example you can understand the collapse load. When a cantilever beam, if you are adding some load at the free end, what happens? It goes from the elastic stage and finally it will going to break. Where it is going to break in the sense, wherever you have hinge point. Where is the hinge point here? You have at the support. So when the load is extreme, before breaking, the plastic hinge will be formed at the joint. So this is the joint, you will be having some plastic hinge here. Okay. Now if you have this, so what is this type of beam here? This is a overhanging beam. You have two supports. What are they? Both are hinged support. So this is one hinge and another hinge. You have two hinged support, and if you are loading, when you keep on making the load, the plastic hinge will occur at this point, that is the hinged point here. Why it is not happening here in the sense, since this is a simply supported or hinged joint, you will be having zero moment at one point. Only at the other point you will be having the moment, that is the negative moment. So this point takes the load. Only one support will take the hinges. This support is going to take the hinge. Okay. When you are loading like this, if you are having any hinge in the cantilever beam, at this point, if any cross sectional change are there, at that portion you will be having the hinges. Okay. Next, these are the example of single span beam, that is a simply supported beam. If it is carrying a point load, the hinges will be there at the point load. Now I will say the conditions, you note it down, the points where you have the hinges. The plastic hinge normally occur at the support. So from this point you can understand that hinges will only occur at the supports, not in the other area. The points of concentrated load and the points where cross sections are changed. So this is important, you can underline this. Where you can find the plastic hinges, first stage is at the joint, second at the loading points, third at the places where you have cross sectional change. These are the three conditions for plastic hinge. The location of plastic hinge in a beam with a uniformly distributed load is however not well defined. So if you have point load, you can indicate that below the point of the load you will be having a hinge. But if you have uniformly distributed load, there you can take the concentration of the load. So for that case, you have to deal case by case. You have to find for case by case, hence it is not well defined uniformly. If you have plastic hinges and if the load attains the maximum limit of the section, then it is visible to see the plastic hinge. If you observe this picture, you can understand that. In the first picture of the single span beam, you can see that do you have the load at center point, hence you are having the plastic hinge at the center point. So what about the next shape? You have a load and you have plastic hinge at that shape. When you have a fixed end, you will be having a plastic hinge. When you have a simply supported, you will be not having the plastic hinge at that point. Hence, at this point you are not having any hinge. The hinge is there at load at the support. How many hinges are there at this section? At the point of load, you will be having one hinge. And how many fixed end are here? Two fixed end. And totally how many hinges should happen? 2 or 3? See, what is the definition here? The plastic hinge normally occur at the support. Okay, how many supports are here? 2 support. And how many loads are here? 1 load. So totally 3 numbers. So you will be having 3 number of hinges. Okay. Now at this case, how many hinges will be there? How many supports are here? 2 supports. Is the support a fixed or hinged? Hinged support. Does hinged support have any plastic hinge? According to the notes, no. How many point loads are here? 2 point loads. Does point load carry hinges? Yes. So you have 2 hinges at this section. Okay. Now take this example. How many supports are here? 2 supports. And what is the type of support? Hinged support. Hence you don't have any plastic hinge. And how many point loads are here? 2 hence you will be having 2 number of plastic hinges. Okay, now take down this example. This is a continuous beam. For a continuous beam, which portion you will be having negative bending moment, you have to consider as a plastic hinge. This case is for continuous beam. Okay, now is this a continuous beam? Yes. How many supports are here? 1, 2 and 3. Okay, all are hinged support. Since 3 hinged support, you will be not having any hinge at the hinged support. But where are the portion you will be having negative moment? Do you have negative moment at this support? No. Do you have negative moment at this support? No. And do you have negative moment at center support? Yes. So you have hinges, plastic hinge at this point. And how many point loads are here? 2. So totally how many plastic hinges will be here? 3 numbers. Okay, tell me for this shape. Tell me for this case. How many plastic hinges are there? Simply you tell the answer. 3 number of plastic hinge for this kind of problem. 3 number of plastic hinge for this kind of problem. You have 1 number of plastic hinge.